Welcome to this fourth part of my lectures on dynamics of a system of particles. In this video, we will study angular momentum methods for a system of particles. Before doing that, let me point out something that I missed in my lecture on work energy methods, and that thing was that change in potential energy due to gravity for a system of particles can be written like this in terms of change in position of center of mass of that system. This is very easy to derive. You can easily get this relation by first writing change in potential energy for a single particle and then summing it over all the particles to get this relation. Now let us come to the angular momentum part. Okay, so for defining angular momentum of a system of particles, let me draw a schematic diagram. So there are various particles in your system. So say this is ith particle which has velocity vi, mass mi, and external force acting on this particle is Fi. Suppose that this is your jth particle, so its mass will be mj, velocity vj, external force fj. Now these two particles also apply force to each other, so that force is denoted by Fij, force on ith particle from the jth particle, and equal and opposite force due to Newton's third law, j comma I. Now let me write angular momentum for a single particle. So for that we need a reference point. Let us take our reference point A here. So this is position of the reference point and this is position of the ith particle, and this is relative position of ith particle from the reference point. So this is Ra, this is Ri, and this is Ri minus Ra. All right. So angular momentum with respect to point A for the particle I let us denote it like this. So angular momentum of I with respect to point A is cross product of Ri minus Ra, the relative position vector of ith particle with respect to A, cross mvi. Great. Now we have to sum this up to find angular momentum for the whole system. So this is for ith particle. This is for the whole system. So for the whole system, angular momentum with respect to point A is given by summation over all i's of angular momentum of individual particles. Now we want to relate the rate of change of angular momentum to the net moment applied to the system. So we are interested in taking time derivative of this. So taking time derivative, HA dot will be so taking time derivative of this first term will be Vi minus Va, velocity of I minus velocity of A, cross we will keep this as constant, plus now we will keep the first term constant and take derivative of the second term. So derivative of V will be A, acceleration, so this will be AI. All right. Now when you will open brackets HA dot, so this term when it gets cross product with this term, so this term will go 0, Vi cross Vi will be 0, and what will be left will be minus Va cross Vi. Now this Va is a constant, so it can be taken outside summation. Constant in the sense that it does not change with I. This is Mi, this is Mi, mass of the ith particle, that has to be there everywhere. This is also Mi. All right. Now what is this term? This second term, so this is m into ai is nothing but from Newton's second law. For a particle, mass into acceleration is net force. So forces are Fi plus summation over J Fi slash J. So MAI is this. Now since MAI is this equal to force, and you are taking its cross product with the force arm, so what you have is basically sum of all moments acting on the system. So these are all the forces which are acting in the system, and you are taking the cross product with their force arms and summing them over. So this is net moment acting on the system. So I will write here M A, and that moment is taken with respect to this point A. Okay. Now notice one thing, that in this moment contribution of all the internal forces will be zero. Why? Because they are acting in a line, they are equal and opposite in magnitude. So the moment of these forces, the force, when you will add them up, its contribution will be zero. So what will be left finally will be net external moment. So moment due to external forces, net moment due to external forces, because moment of equal and opposite forces will cancel out. So there will be no contribution in moment from the internal forces. So if I want to get a relation which is analogous to my relation for linear momentum, that is, for linear momentum I have L dot is equal to sum of all external forces, something like this, then I have to make this term 0. So when this term will be 0, so my final relation, this HA dot is equal to net moment due to external forces, is valid for two cases when this term is 0. So this term is 0 when either VA is 0, this implies A is fixed. So when you are calculating angular momentum with respect to a fixed point, then this relation rate of change of angular momentum is equal to net external moment will be valid. And another way in which this relation will be valid is when A is center of mass. When A is center of mass, what will happen is VA is equal to VCM. And if I look at this term VA cross MI VI, I have talked about this in several videos, that this is basically mass into velocity of center of mass, because this is linear momentum. So this is total linear momentum L, and it is given by, we have already seen, MVCM. So this is going to be VA cross MVCM. And when VA is equal to VCM, this term, let me call this term as X. So this X is 0. So I will write the final relation for you. The final relation for angular momentum is H with respect to A, rate of change of angular momentum, is equal to net external moment with respect to the same point provided A is fixed or A is center of mass. Now from this you can also write all the impulse momentum and momentum conservation laws. So you can write HA2 is equal to HA1 is equal to integral of addition ma dt, angular impulse for the system. All right. So this is JA, and if external moment, net external moment about some point A is 0, then angular momentum is conserved about that point, provided that point is either center of mass or a fixed point. All right.